Hey, welcome back to Fat Mama Physics. In this video, we are going to do some examples on discharging and the charging of capacitors. Okay, so for this one is 11.3b. So let's get started right away. Okay, 10 microfarad capacitor, that's a huge one, is discharged through a 12 kilo ohm resistor. So in a schematic diagram, what that would look like is you have a capacitor and it just got charged, and then someone closed a switch between the capacitor hooked up with this resistor so that the all that charge stored in the capacitor will be used up by the resistor to power something up. Maybe a Tesla coil, I don't know. So here we got 10 microfarads over here. Here we got 20 kilo ohms. Let's go ahead. Okay, what is the time constant for the circuit? Okay, so time constant is, in fact, we're going to learn about time constant in B, so I'm going to save that for a bit. But essentially, the time constant is a number that dictates how fast a capacitor discharges. So the smaller the time constant, the faster it's going to discharge. So that is what it is. And guess what? The time constant is going to depend on the resistance, and it depends on the capacitor. So, meaning if you have a large resistor, it's going to take longer since there's more resistivity in the circuit for current to flow, and also the larger the capacitor, meaning it has the ability to store more charge, also will increase this time constant, meaning it will take longer for the capacitor to discharge. So I really like that. It's very intuitive there. So that is the equation. It's also in your data booklet. You don't have to worry about that. So let's go ahead and calculate this time constant. We have 10 times 10 to the power of negative 6 farads, which is the micro, and then 20 kilo ohms is 20 times 10 to 1,000 ohms here. Did I say ohms before? Sorry, that was farads. Okay, so after we calculate this out, I get 0.2. I get 0.2 seconds. Or, I guess there's no significant figures, so I'll just write 0.2 seconds, which is also 200 milliseconds. It's the same thing, okay? Moving on to B. This is the interesting part. What is the fraction of charge remaining after one time constant? So one time constant is just going to be 200 milliseconds, or 0.2 seconds. So the time constant is, hopefully you've found it obvious, it's the unit of measurement of time. So what we want to do is we want to go find the discharging equation for the charge of a capacitor. So if you learned the decay equation in math, that's fantastic, but if you have not, it is provided in your data booklet. So Q equals Q naught, and think of naught as an initial. Okay, or if you want to just say maximum charge, you can also think of that as well. It's the maximum charge that is stored in the capacitor, and it all degrades over time. Here we have T over tau, which is the time constant. Okay, so if we put that over here, Q is equal to Q naught E negative to the power of negative T over tau. This, when we say the fraction of charge remaining after one time constant, it means that the time is just going to be equal to tau, okay? Which means that this equation is going to simplify to Q. Actually, you know what? Since we're asking for the fraction, I'm just going to divide the Q naught to the other side. E to the power of negative T is going to be tau. So we get tau over tau, and essentially that's just E to the power of negative 1, okay? So let's just write E to the power of negative 1, and guess what? Let's calculate E to the power of negative 1. And I already know what it is, but I will just do it in front of you because I don't know what. Okay, so here we go. E to the power of negative 1 is 0.3678, and that goes on. But essentially, that gives us 0.37. That's the fraction of the charge remaining on the capacitor after one time constant. So that time constant has an interesting, produces an interesting value because it allows this E to the B to take it to the power of negative 1, which E has a specific value, which is 2 something, I forgot, 2 point something. So that's just what another part of the definition of the time constant. It it also means the amount of time it takes for the amount of charge to drop to 37% of its original. So that's something interesting there to talk about the time constant. So it's not just RC, it's the time also for the charge to decrease to a certain value. Which also leads us to example 8, because we can also talk about something called a half-life, which we will learn in the nuclear unit, or you may have learned already, or you may have learned in a previous science course. The half-life is the time it takes for exactly half of the charges to be lost on your capacitor. Or another way, it's a time value. It's a time that it takes the charge on your capacitor to half itself. So on this graph, what that means is, that's Q. So that's RC right there. So this is going to be 0.37, and half of that, which this graph looks terrible at that, it's about here, hopefully. So that's going to be 1/2. So this value down here is going to be the half-life, okay? So this is the half-life. It's a time, okay? Just like the time constant. Time constant is a measurement of time. The half-life is also a measurement of time. So I'm going to write half-life right here. This is going to be, so there, T, it gives us it there already. So we want to show that the half-life is related to tau, time constant, times ln of 2. So how do we show that? First of all, let's just take the generic charge equation. Q is equal to Q naught e to the power of negative t over tau. Well, we know that we're looking for the half-life. So we're just going to directly use half-life instead, okay? So half-life is going to be t 1/2 over tau. The other thing I can do here is I can get Q naught over Q on the other side, because by definition, if we want the half-life, we want this fraction here to be exactly 1/2. So we're gonna do that right now. I'm just gonna put that on the other side. Okay. So then what we're left over is we're going to be left with Q, we're going to be left with Q over Q naught. This is going to be 1/2 and times, or equal, to e to the power of negative t half-life over tau, okay? So now if we want to solve for t, the half-life, we need to do, we don't need to care about the tau. The tau is just a constant, it's just a number. But what we want to do now is we want to take the ln of both sides. So basically, if I did that, I take the ln of the entire equation. Taking the ln of the entire equation, let's do a thing here, is going to look like this. I'm going to continue my work over here, okay? So that's going to look like ln 1/2 equals to ln of e to the power of negative time, that's the half-life t divided by tau, okay? So what this looks like here is, how do I get this to look like that? Well, first of all, this is going to simplify. And since I also want, I want ln of 2, I don't want ln of 1/2. But if I want to do that, I could do this. This is essentially 2 to the power of negative 1, which is also 1/2, right? So I could do that, which is equal to, and I could do, if I have ln of e, then my exponent pops out in front, which is just negative t half-life divided by tau. So let's just do that divided by tau very neatly, and then this is ln of e. We know that ln of e is actually just 0. Ln of e is 1, not 0, my bad. And also, I'm going to pop out the negative in front here with the 2 to the negative 1. So I get negative 1, or negative ln, and in brackets 2 is equal to negative the half-life divided by tau. And since ln e is just equal to 1, that just disappears from my equation. Now I have 2 negatives on both sides, which I just make them positive. And hey, this is looking a lot more like what we need to get to at the end. The last step is going to be me multiplying my tau to the on both sides of the equation to get rid of the tau here on the bottom. And finally, I'm going to get half-life, which is t here, t half-life, is going to be tau times ln 2. Okay, so there you go. Woohoo! Woof! There we go. So that's showing the relationship between the time constant and as well as the half-life. Okay, so whenever you're trying to solve for points on a graph, these are two interesting points you could plot. One of them is the time constant and the other one is the half-life. Okay, so I don't believe half-life is given in your data booklet, so you probably need to know how to derive it. So the mathematical, you do need to know your logarithms and your natural lns. All right, so that's question 7 and 8. I did want to go over one more, which is this one. Hopefully it won't take too long. It is also in your coursework example, but alas, let's just quickly go over it. The graph on the right shows a variation with time of this charge Q on a capacitor plate as the capacitor is being charged in the circuit. The capacitance is 4 microfarads and the resistance of the resistor R is 2 kilowatt. Sorry, not 2 kilo ohm, okay? So we have, so it is being charged up, meaning it must, this entire setup must be connected to some sort of battery here. Okay, so we got a battery, it's connected to a capacitor over here, and it's also getting, this resistor here is also attached in series. Use a graph to estimate the EMF of the charging battery. So we do have, okay, so based off of this graph, I was going to calculate the RC value, but we can do that in due time. So to find the EMF of the charging battery, this means that using the resistor, I can find the maximum current to find the EMF. So near the beginning of the charging process, which I don't have the maximum current. It's not given to me in this question. The only other way I can figure this one out is I would have to look at the end of the charge. End of the charge, there will be no current flowing. Oh, sorry. If there is no current flowing at the very end, then the potential drop across my resistor is going to be 0, meaning that the potential gain in my battery, the EMF of my battery will be exactly the same as the potential developed across my capacitor near the end of the charge. So to find that, I need to know the maximum charge stored on my capacitor. So the charge that I got at the very end. So it looks like this point here, which is 36 microcoulombs. So the maximum charge stored is 36 microcoulombs. I know the capacitance, so to find the voltage across my battery is going to be Q over C, which is going to be exactly the same of the EMF at the end of the charge. So 36 microcoulombs over the capacitance, which is 4 microfarads. Ooh, that's very nice. Micro cancels out, and this is going to give me 9 volts. Oopsie, it's not Q. 9-volt battery, which makes sense. So that number makes sense. Okay, so that's E. A is done. Okay, time to try out B. So A, this is B. Sketch a graph to show the variation with time of the current in the circuit while the capacitor is being charged, putting numbers in the vertical axis. So this is suggesting that we want to be specific in our values. So if we do, there's a couple points that are interesting. So what if we just did this? Okay, I'm just going to draw a basic sketch of this graph. I know that the time is going to be on the order of the milliseconds, about 50 milliseconds. So if we divide this up relatively equally, hopefully, 1, 2, 3, 4, 5. So this is 50. This is in time in milliseconds. And what do we want? We want to find the variation of time of the current in the graph. Okay, so current versus time. Okay, the current, that's gonna be, we know that the current starts out with a peak and then it drops off because over time, as the potential difference develops across this capacitor, it's gonna start to it's the potential drop across the resistor is going to be less and less, meaning less current will be flowing. Okay. So what we could do, well, we know that the current at 50 is going to be 0. So let's just put that one dot there because we know that for sure. To find out the initial current, we know that the maximum current is going to be, so I'm just going to do Imax. Get it, Imax. It's going to be the potential, the EMF of the battery, which is going to be 9 volts, over the resistor, which is 2 kilo ohms. So 9 over 2,000 ohms, 9 volts over 2,000 ohms is going to be 0.0045, 0.0045 amps, which is just 4.5 milliamps. So when I plot this graph, I'm probably going to make this 5 and 5 milliamps. So this is my current measured in milliamps. This is going to be 5, and dividing this one relatively equally, 1, 2, 3, 4. Oh, that's gross. I'm so sorry. This is bad. That's going to be here, 2, 3. Okay, that's a little bit better. So that's going to be 4. I'll write it here. 4, 3, 2, 1 milliamp. We start off with 4.5 milliamps. So we start right there. That's our starting point. So establishing the starting point and the ending point is very important. And the other point, there's actually 2 more points on this graph we could plot. One of them is the half-life. The other one is the time constant. So I'm going to use this part. I'm just going to use this graph here just as extra space. So based off of our derivation before, we know that half-life is equal to the time constant times ln of 2. Well, there you go. We need time constant. So to find the time constant, we need RC. Okay, RC is given to us 4 microfarads, which is our capacitor. Oops, opposite direction, opposite order, and 2.0 kilo ohm. Okay, so if I multiply those together, I get 8 milliseconds. Okay, so this is going to be 8 milliseconds. Oof. So if this is 10 over here, 10 milliseconds. 8 milliseconds is about right there. And that's, remember, the time constant is the amount of time it takes the charge or the current to drop down to 37% of its original value. So 37%, let's just quickly do that. 37% of 4.5 milliamps. So if I'm just doing this calculation right here. Milliamp 0.045. This is 1.665. 1.665 is going to be right about here. Okay, so that's 1 point on the graph. So that's our time constant. Okay, the other thing is that we now have the time constant. We can use that to calculate the half-life, which is the time constant 8 milliseconds times ln of 2. So let's do that. This is going to give us 5.54 milliseconds. So I know this is not making much of a difference. So about oopsie. You know what? Let me just write this down so you know what it is. This is 5.545 milliseconds. 5.54 milliseconds is about right about there. And for half of 4.5 is 22 or 2.5. 2.5 is 22. 2.25 is roughly about there. Okay, so those are just I just plot that in. That's just half-life. So now I have these 2 points. You're like, oh, did that make much of a difference? I know. But here we go. This is a rough sketch. Okay, so I go through these 2 points and I make sure it goes, it goes all the way down to 0 at the end. Okay, so I can try to do a better job. Good enough. Okay, so there you go. That is my rough sketch. So, just to recap on that, find the beginning value, find the end value, and probably at least 1 or 2 points in between, which is a good, easy one is to find the time constant. for that matter. So notice that in order to do these questions, you really have to understand the process of charging a capacitor and discharging a capacitor, which I highly recommend. Again, the FAT simulation for AC on from Colorado, which is fantastic. So hopefully this was helpful in getting you started. So I thank you for watching, and Fan Mama Physics signing up.